Unit 3, Video Lecture 4, Quantum Theory, an Introduction to Electron Configuration. Niels Bohr introduced us to one of the most recent models of the atom. In his atom, he pictured the electrons orbiting around the nucleus, much like planets did orbiting the sun. This is a picture of his atom. Even as he introduced his atom, he was concerned with the fact that as he tried to apply his model or his theories to larger and larger atoms, his model would start to fall apart. So he knew it wasn't quite right. He did, however, introduce one of the most important ideas of the 21st century, and that is the idea that electrons exist in quantized or set fixed energy levels. This whole idea of quantized energy levels gave birth to a new science called quantum mechanics. Bohr admitted he was wrong. Bohr amended his view of the atom by saying that electrons don't orbit the nucleus like planets orbit the sun, but they act more like bees buzzing around a hive, constantly in motion. From his theories, along with several others, we have the modern atomic theory, which is called the quantum mechanic model. And in the quantum mechanic model, the nucleus, which consists of protons and neutrons, are surrounded by an electron cloud. Basically, a place where the electrons are constantly buzzing around or constantly moving in. The clouds describe the energies that an electron can have and where that electron is most likely to be found. Werner Heisenberg also came up at the same time with something called the uncertainty principle. What Heisenberg said is that one cannot simultaneously determine both the position and the momentum of an electron. You can find out where the electron is going or where it is, but not where it's going. And you can find out where the electron is going, but not where it is. So if I can't figure out where an electron is going or where it is, can I at least find out where the electron is most likely to be? Introduced Erwin Schrodinger and Schrodinger's wave equation. What this equation predicts is the probability of a single electron being found along a single axis. Now in three-dimensional space, there are three axes, x, y, and z. In order to know where approximately, or the probability of where the electron is, you have to solve this three ways and then look at where they all intersect. And that's for one single electron. Of course, we do this by computer today, and here are some of the pictures of electron clouds that we have that are computer generated. Pretty cool, huh? What Schrodinger also theorized was the whole idea of quantum numbers. He said that electrons do exist in a three-dimensional space, but they're constantly moving. In order to describe the movement, we need to have a quantum number. And there are actually four. In order to describe where an electron is, or the movement of an electron, at any single point in time, we need four quantum numbers. The first three describe where that electron is in the three-dimensional space, and the fourth describes the rotation or spin of that electron within that space. So what exactly do we mean by that? Well, it's kind of like you. You have an address. You live in a state, and if we further narrow that down, the state, we can look at the city that you're in. The city is divided up into roads or streets. And on those streets, we find one number. That's your address. That's where you exist. Electrons are the same way. They have their own addresses. But in this case, the primary or the most general address is the shell that they exist in, or their energy level. From the shell, we can also further divide that into sublevels. Sublevels can be further divided into orbitals, and orbitals into the spin. This describes the four quantum numbers for every electron. So let's take a look at those quantum numbers. The first quantum number, which is the most important for us, is called the principal quantum number. Another way that it's portrayed is with just a small n. This describes the energy level that the electron is in, or aka also known as its shell. In theory, there's an unlimited number of energy levels, but in reality, on the planet Earth, all the substances that exist on Earth are in energy levels that range from 1 to 7. If we marry up Bohr's model with this whole idea of energy levels, what you can see is that his orbits around the nucleus can be translated into an energy level. There's a fixed number of electrons that can fit in any energy level or in any shell, and that's designated by this equation, 2 times n squared. So if we look at each energy level in the first energy level and we solve that for the number of electrons that can exist in the first energy level, we find that 2 electrons can fit in the first energy level, or 1 squared times 2 is 2. In the second energy level, where n equals 2, 2 squared times 2 is 8. So in the second energy level, we can fit a total of 8 electrons. In the third energy level, we can fit 18. In the fourth energy level, we can fit 32. And it just increases from there. The second quantum number is also known as the momentum quantum number. Now, in general, this is usually symbolized by a letter L. That designates the orbital or the subshell in which the electron is located. We study 4 sublevels. The first one is an S sublevel. This always holds a maximum of 2 electrons. There's also a P sublevel, which holds a total of 6 electrons. A D sublevel that holds 10 electrons, and an F sublevel that holds 14 electrons. The third quantum number, called the magnetic quantum number, is symbolized by a letter M. And what this tells us is the orientation of the electron within the orbital itself in relation to the 3 axes. So, within the S sublevel, we have 1 orbital. 1 orbital can only contain no more than 2 electrons. That's why the S can only have 2 electrons. The P, however, has 3 orbitals, each potentially containing a maximum of 2 electrons for a total of 6. In the D orbital, or the D sublevel, there's 5 orbitals. Again, each holding 2, potentially holding a total or maximum number of 10 electrons. In the F sublevel, we have 7 orbitals, holding a total of, maximum total, of 14 electrons. The fourth quantum number tells us which way the electron is spinning or rotating. It can either be clockwise or counterclockwise. This is the same idea of the fact that planet Earth rotates on an axis as it's simultaneously rotating around the sun. Since there are 2 possibilities for spin, we label that as either plus 1/2, that's clockwise, or negative 1/2, counterclockwise. Usually we show that with arrows pointing either up or down. Here's a table of quantum numbers for the first 4 energy levels. No, you don't have to memorize this. Again, this is just an introduction to the next video lecture. And when we look at the quantum numbers, they provide for us the rules of how the electrons are placed around the nucleus of the electron. Why are quantum numbers important and quantum mechanics is important? Because it helps us understand the behavior of the electron. It's the electron that's involved in bonding and interactions with other chemicals. It's the electron that determines what kind of compounds are created from the various elements. So if we understand the electron and how it behaves, we have a better understanding and we can predict how compounds are going to be created and how elements and compounds will interact with each other. From quantum mechanics, we get 3 rules to electron behavior. The first rule is called Aufbau's rule. And what this says is that electrons will seek the lowest energy levels possible. The lowest energy levels are the ones that are closest to the nucleus. Therefore, electrons will fill energy levels from the lowest or closest to the nucleus before they'll move to the higher energy levels. The Aufbau principle was put together by Wolfgang Pauli and Niels Bohr together. Pauli also came up with a principle called the Pauli exclusion principle. What he said is that no 2 electrons can have the same 4 quantum number. Therefore, within the orbital, each of the 2 electrons that are within that orbital must be spinning in opposite directions. Last, we have Hund's rule. This was put together by Friedrich Hund. When sharing an orbital within a sublevel, electrons will stay as far apart as possible, filling all the orbitals first, spinning in the same direction in that sublevel before doubling up, so that you can have, remember, how many can you have in an orbital? You can only have 2 spinning electrons spinning in the opposite direction. Let's marry this up with something that's a little more familiar, periodic table. Well, if you look at the organization of the periodic table, it reflects this information. If you look at the rows called periods across the periodic table, and I count them, I have 1, 2, 3, 4, 5, 6, 7. The periods or rows on the periodic table are also equal to the energy level, the principal quantum number. If I further separate the periodic table, what I can find are the orbitals. In the first 2 columns, I have the s orbital. This also includes the first period, the last one on the first period, or the 1s. The p orbitals are in the last columns of the periodic table. The middle columns are the d orbitals. And the final 2 are the f orbitals. We'll talk a little bit more about the organization of the periodic table in a later unit. What you want to see here is that if you look at the first 2 columns, which are the s orbitals, I only have, as I move from left to right, 2. And remember, the s orbital can only contain 2 electrons. If I look at the p orbitals as I move from left to right in the same period, I have a total of 6 squares, or 6 electrons. That happens to be the total number of electrons that can fill that p orbital. The d orbitals, if you remember, can hold 10. As I move from left to right on the periodic table in a single period, for example, period 4, if you move from left to right in the d section, you will find that there are 10 squares for 10 electrons. If you move to the f orbitals at the bottom, as you move from left to right and you count the squares, you will find that there are, that's right, 14 electrons. At the conclusion of this video, there is a link to a Google Docs quiz. Be sure to take that quiz before you move on. Thanks for listening.